voy a compartir la pantalla para que el Héctor Guerrero tome la palabra.
Gracias. Voy a hablar en inglés para agradecer a los profesores Wada y Takeuchi. Thank you very much, Professors Wada, Professor Takeuchi, for being with us today. We really appreciate your consideration and the time you dedicate for this session. Thank you very much. I will read a brief bio from Professors Wada and Professors Takeuchi. I will do that in Spanish. Voy a leer en español las semblanzas de los profesores. El profesor Wada es profesor emérito del Instituto de Tecnología de Tokio y una de las figuras más influyentes a nivel mundial en el desarrollo de sistemas estructurales sismorresistentes. Es reconocido por ser parte del equipo pionero que desarrolló los contraventeos restringidos al pandeo en la década de los 80 en Japón, tecnología que ha transformado el diseño sísmico a nivel internacional. A lo largo de su trayectoria, ha contribuido significativamente a la investigación, desarrollo y aplicación de sistemas de disipación de energía y control estructural, participando en múltiples proyectos emblemáticos y en la formulación de lineamientos de diseño sísmico. Su trabajo ha tenido un impacto decisivo en la ingeniería estructural moderna, particularmente en el desarrollo de soluciones innovadoras para mejorar el desempeño sísmico de edificaciones. Podemos ir a la siguiente, Vania. Muchas gracias. Por otro lado, el profesor Toru Takeuchi es profesor también del Instituto de Tecnología de Tokio y un referente internacional en ingeniería estructural y diseño sismorresistente. Su trabajo se ha centrado en el análisis y desarrollo de sistemas de control estructural y disipación de energía, así como el estudio del comportamiento sísmico de edificaciones complejas. Ha contribuido de manera importante al avance y aplicación de tecnologías como los contravientos restringidos al pandeo y otros sistemas innovadores para mejorar el desempeño sísmico. A lo largo de su trayectoria ha participado en múltiples proyectos de investigación y desarrollo y colaborado en la industria para llevar soluciones avanzadas de ingeniería a la práctica profesional. Su labor académica y profesional lo posicionan como una figura clave en la evolución del diseño estructural moderno a nivel internacional. Y con eso, pues me gustaría agradecer mucho su participación, que hayan aceptado estar con nosotros desde Japón. Ahorita para ellos ya es miércoles allá por la mañana. Y pues muchas gracias por el esfuerzo de estar muy temprano allá en Japón y compartirnos sus experiencias. Gracias, profesores, y adelante les dejamos la pantalla por si quieren compartir su presentación.
Okay, thank you very much. Very kind introduction to me and Professor Takeuchi. And today I'd like to discuss about BRB, birth, theory, and spread worldwide. Please, next slide. When the bridge has a large slenderness ratio, the deformation capacity is sufficient for tension load. But これちょっとProfessor Takeuchi,
Yes.
too wide. Okay.
Right.
Oh, okay. But lateral buckling occurs easily under compression, and the brace cannot bear compression forces. It will show slip type hysteresis and repeated loads and during earthquake. And when the brace has medium slenderness ratio and certain axial forces, brace bears tension force and compression forces. Unfortunately, the brace buckled under high compression. The behavior is very unstable, and the brace will be broken under next tension. Okay. When the brace has small slenderness ratio, it can also bear the compressive load and tension load, and the buckling will not occur. However, brace's axial force stiffness and strength would be very too high. The very difficult to design column and foundation. There are many difficulties in designing the surrounding columns and foundation structures and the significantly large forces caused by too strong braces. Okay. Please. And if the problem of the buckling is solved, it will be possible to design the appropriate stiffness, appropriate yield strength, and yield deformation. That's why many structural engineers in the world were waiting for the BRB. Thank you. Next. This test was done in 1987, and next year will be 40 years anniversary of the development of this BRB. Next, please. There are 5 specimens. Bottom is the most stiff tubes, and the top is the most weak and flexible outer tube. The Euler buckling load of the outer tube divided by the yield force of the core member. The bottom is 3.53 and the second is 1.39 and third is 1.05. These 3 specimens not buckle, very beautiful tension and compression deformation capacity, but Euler buckling load of the tube divided by yield force, the 0.75 and 0.55, very not good performance. But these 5 specimens, core member is the same. The outer tube is different. Okay. Next. Okay, please start, Professor Takeuchi.
Thank you very much, Professor Wada. Okay, I will explain later a part of this presentation. I'm Toru Takeuchi. So we have organized the textbook for the Buckling-Restrained braces issued in 2017 from Japan Society of Seismic Isolations called Buckling-Restrained Braces and Applications. Later on, I talk about the contents included in this textbook. So basically, as you know, the composition of the Buckling-Restrained brace is basically the concept is core plate is restrained by the buckling restrainer. In many cases, steel tube with mortar infill. And there is the debonding materials is attached between the core plate and the restrainers. That is slipping in the compression slipping in the restrainer without transferring the actual force to the restrainer. So that makes the pure compression for the core plate after yielding in the same the tension forces of the tension yielding. So that causes without any the overall buckling is prevented by this restrainer, but their stiffness is same as the core plate. So that makes more very simplified the asymmetrical the hysteresis in the compression tension. So there is this is appearance of the typical BRBs, and some of the compositions, some of them is steel tubes with concrete infill or mortar infill, or sometimes is double tubes or dry type BRB are also produced. And even the core plate is compressed within a restrainer. They try to, there are some small gaps allowing the expansion of the core plate with a Poisson's ratio. So in these gaps, the bonding gaps, there the core plate is try to buckle within a restrainer, and to touch on the wall of the restrainer. Then they move to the higher buckling mode. Then afterwards, they reach it to the yielding forces, and then after that, they have a very symmetrical compression tension, the hysteresis group. And the first application of the Buckling-Restrained braces is the unbonded braces developed in 1987, and the first installation is 1990s in Nippon Steel headquarters in number 2 in Tokyo. So that is, as Professor Wada said already, almost 40 years has passed from the first development. And after that, in 10 years, in 1990s, there is a many application was expanded in Japan. And in 1997, there is a huge buckling restrained brace of the length is reached to 20 meters was applied to this Jumbo BRB for the Osaka International Convention Center. As before that, there is some the concept of damage tolerant design was proposed by the Professor Wada and Professor Kona or others, and that makes a structure is divided into main frame supporting a vertical weight with replaceable energy dissipation braces. So when conventional the seismic design is allowing the main structure to be yielded in the beam end and the column end, and that makes after the earthquake, the structure itself is damaged. But this concept try to keep the main structure supporting vertical weight in elastic for the larger earthquake, and to displace all the input energy by the this additional energy dissipation braces. That doesn't supporting a vertical weight. That be can be replaced after the hard severe earthquake. So that makes all the building property can be secured in safe. So continuous occupancy can be achieved. So this is a damage tolerant concept. So then after the introduction to the United States in late 1990s, the first this techniques is transported to the United States. So the first application in San Francisco or California was started in early 2000. So the first application is plant environmental sciences in UC Davis, and also there's many the retrofit works in the hospital on the federal building, like in Salt Lake City in the right side. The BRB's types is, as I said, typical one is the Lloyd strength steel is a core plate with debonding materials together with a restrainer in sometimes rectangular or circular section, and the infield mortar is in between. And another type is double tubes. That is internal or outer core the tubes is yielded, and while the outer tubes or inner tubes is preventing the buckling. So kind of a double tube system. And the another type is the core plate is covered by the channels or the cross sections. That is called the dry type of BRBs. So that is also the developed and typically in the practice. So here I'd like to show you some the example of the shaking table test of the BRBs. Here, the 200 tons of the weight is sitting on a seismic isolated rubber bearing and produces 2-second shaking the model. And then our whole system is sitting on a shaking table and to apply the dynamic forces into the BRB. To look at here, they have a big movement, but there is actually a continuous, the displacement is distributed into the this length in core plate. That makes, but there is no buckling occurred. Okay. So the simple the logic is simple for the BRB, but we have to be care of the if the restraining the condition is not good, local buckling occurred in the typical part of the limited part of the corporate. Sometimes a local bulging to pushing the wall of the restrainer it makes hold the instability. So that makes sometimes the degradation of the compression side in hysteresis. And sometimes because of the friction, the ratio of the compression and tension is becoming larger. So that could be called a beta factor in the strength, yield strength of the compression side divided by the tension side is usually well-designed BRB is less than 1.2, but it sometimes reaches to the 1.5 or more. So that is not so good for the characteristics of the BRBs. So when you using the connection, if the pin types in the pin the connections, there is some slackness or sometimes occurs also. So for the restrainer design, we need to care about various types of conditions. So these are the different types of the failure mode. Most the preferable the fracture is fracture by the Lloyd's low cycle fatigue failure. But before that, sometimes it's called by the global instability, including the connections, and also the higher mode buckling causes the local bulging sometimes. And sometimes a connection is a failure before the BRB is to complete dissipating energy. So restrainer is firstly successfully need to be suppress core first mode buckling. So that is to explained in chapter 2 in my the textbook. And the debonding mechanism decoupled actual demands and allows for Poisson's effect. That is how to design the thickness and materials of the debonding layers. And the third is the restrainer wall bulging. So due to higher mode buckling inside the corporate the restrainer need to be suppressed. That is explained in chapter 3. And the global out-of-plane stability is ensured, including a connection. That is this part. It's instability, including a connection without that is because of the unrestrained part is sometimes lead to the instability. And the low cycle fatigue capacity is finally he decided how many cycles they can be to stand with. Okay. So first, restrainer design need to be basically read by this formula. This formula is maximum actual force, including hardening. It's defined as NCU. And usually that is a coiled force amplified by the overstrength and the strength hardening. And it's a minimum the yielding the strength. Stress multiplied by 1.4, 1.5. That is multiplied by the A2SE. That A is fabrication tolerances. That is a kind of perfection. And the S is clearances or thickness of the bonding materials. It's doubled. And E is the eccentricity of the axial force. These are the eccentricity multiplied by the axial force is to form the maximum demand for the bending moment for the restrainer. And including second order effect of the NCRB is Euler buckling strength of the restrainer given by this formula that is famous. And the EIB is restrainer's the bending stiffness. And the LB is restraining length. And that was to be divided, the NCU divided by NCR is 1 minus this value is called as a second order effect. And this formula forms the bending demand of the restrainer. So that is should be less than the MYB, that is the fracture strength of the restrainer. But this formula can be simplified where initial imperfection is smaller and the relatively slender restrainer with this condition. And with the overall safety factor of alpha E is 1.5, it can be simplified the maximum axial force with some safety factor or 1.5 or 2 is smaller than Euler buckling of the strength of the restrainer. That is more easy to understand the formula for the design of the PRP. But you need to care about these conditions. And the second issue is to preventing a local bulging failure. So when the core plate is the local buckling inside the debonding gap in the restrainer, they try to push the wall of the restrainer in citing the strength. So in the strong axis, weak axis and strong axis, both formulas can be formed. That should be received by the capacity of the failure mechanism. That is can be calculated with a different failure mode with yielding the lines, and that can be to expressed by these formulas. It's different condition of the estimation with the yielding line. So that causes the bulging effect can be to be explained. So to compare it to the proposed design method is the capacity divided by the demand. The demand divided by capacity is a smaller one, and that is the conditions. And there is some lines of these equations, and that is this plotted point is the result of the past test, and the cross marks is causes local barging failure, and the circular black dot is successfully related to the low cycle fatigue failure without any local barging. So luckily they can cover the lines of the criteria. So the textbook is showing this formula and the result in to preventing local barging. And the another thing is connection design and the global stability. In the AIJ recommendation of the buckling the members is provide that the recommendation for stability design of steel structure in 2090 and divide to expressing two types of the design for the BRB stability. And without that, it can be the yield hinge is produced at the necks of the BRBs without the restraining place. That makes the overall instability occurs before the BRB successfully dissipated the energy. So there are the two types of the model for designing the BRB stability. One is a cantilevered gusset concept that allows the hinges produced at the end of the transfer, the end of the restrainer, and the designing connection as a cantilever conditions. So that can be achieved by the very stiffness at the both end. Otherwise, it can be rotated here, and then that makes easy the instability of the overall system. And the another concept is try to keep the bending moment transfer capacity at the end of the restrainer to grabbing the connection at the end of the restrainer, and that can allow the rather soft connection for the both end. So that makes some stability condition can be satisfied by the restrainer and continuity concept. So both design concept can be expressed in the textbook, and the very typical the BRB configuration is a one-way configuration and the chevron configuration, both affected by the stiffness, out-of-plane stiffness of the gusset plate and the connection joint. So in Japanese, the typical details adding leaves and at the gusset plate, so makes quite stiff, high stiffness details. But sometimes US or New Zealand causes a low stiffness concept that it's a very yield to out of plane. The rotational stiffness is lower rather than comparison with this. So with the very stiff conditions, we can use this cantilever gusset concept. But with low stiffness conditions of the gusset plate, we need to consider about the overall stability check. So the overall stiffness check can be modeled by this kind of different failure mode, and the formula for the M limit is produced by us for these equations. That is some function of the rotational stiffness and the strength of the restrainer end conditions. So for achieving a moment transfer capacity at the end, there needs some kind of the elastic part of the corporate need to be sticking into the restrainer. Otherwise, this kind of the detail is simple pins connections that is very easy to lead to unstable condition, to instability. Okay. So when also the the end of the gusset plate lead to the plastic hinges, and they produce 4 hinges condition. That the stability can be led by the checked by these formulas. So there is a 2 n limit. Limit 1, the limit 2 is to derive the mean is these conditions. When the elastic buckling path is can be applied to this line, this is axial force, and this part is this type axis is the out of plane deformation. So with to instability first the imperfection and of the AR, they produce some the instability elastic buckling path to the NCRB to this line, and also the ultimate strength can be applied to lines like these conditions. So these are in limit 1, limit 2 condition is cross point of the 2 lines. So if the yield of the core plate can be smaller than this n limit, that can be that means BRB is stable without any over buckling. But if the n limit NCU maximum axial strength of a core plate is go over exceed the n limit, then it's going to the stability limit, then to lead to the plastic crack path. So that means unstable. So these formula can be used for the design, the connection design. Okay. So the next topic is low cycle fatigue induced fracture. Fracture of the ordinary tubular members after buckling is very fragile. When if once the buckling occurred, there causes a small the local buckling at the elbow buckling is produced at the very limited part of the tubes. Then after 2 or 3 cycles, they lead to the fracture. And after that, in a tear off in the tension side, that is very, very fragile. So if once buckled, after buckled, it leads to the fracture in very early stages. This is the tower, the the tower in the nuclear plant to receive some the earthquake. So after that, you can see the many of the diagonals is fractured after the some shakes. This can be also the followed by the analysis, and the so circular one is backwards, and the red one means a fracture after buckling. So not only to causes a buckling, we need to think about the fracture after the buckling. So differences between the ordinary tube brace and the Buckling-Restrained brace is can be explained, but in ordinary tube brace after the buckling, they have a local buckling occurred. So then all the energy, plastic stress is concentrated on this very limited part. So that makes a fracture very earlier. And the incomplete buckling restraint braces, they cause some local buckling in a limited part, even though because of the friction. Then a plastic stress concentration is occurred on a limited part. So if a well-designed buckling restraint braces to control the distributed all the plastic stress throughout the length of the core plate, that makes the yielding part is distributed into the whole length of the restrainers. So mid local buckling and average strain distribution along the plastic zone makes a huge capacity of the energy dissipation, the performance until the fracture. So there is a very big difference. So basically, the cumulative energy dissipation capacity until fracture is following those the load the fatigue curve of the steel materials. This vertical part is the strain amplitude, and the horizontal axis is number of cycles until the fracture. In the different types of steels, produce some small differences on fatigue curve, and the BRB's the fatigue line is little bit smaller than these materials. That is causes of the local buckling inside the restrainer causes a reduction of the fatigue performance. So we need to care about this differences is affected by the design of the BRB and the design of the debonding gaps. Okay. Okay, so another issue is for the performance of long buckling restrained braces. When very, very long buckling restrained braces, the debonding material is basically to reducing friction between the core plate and the restrainer. In tension side, it's simply to the plastic strain is distributed along the members, and in the compression, it's going to the higher mode. There's many friction forces produced in along the member places along at the touching point of the local buckling condition. So that makes the strain concentration is occurred at the end of the restrainer, and lesser compressive strain is remained in the center part. In the tension side is evenly distributed. That causes the compression. It's the cyclic the hysteresis is shifted to the compression side at the end of the restrainer. And in the center, the hysteresis is shifted to the tension side. That causes sometimes earlier fracture at the center, or the binding into the restrainer at the end of the restrainer. So in a past experiment, sometimes it's observed that a reduction of the low cycle fatigue capacity for the longer BRBs. And so we have tested in 2 years ago in our university that the long BRB causes really earlier failure or bulging effect. So such a long BRBs, we can to find that this is the gray line is a smaller ordinary BRB, and the red one is a long BRB. And this graph shows a compression tension strength ratio beta, that the compression maximum force divided by the tension side. So ordinary BRBs is this ratio is less than 1.2. But the longer BRBs cases, in the compression side, there is a significant increase in the compressive force for long BRBs. The common binding was observed, and the beta ratio is reached to the more than 1.5. So that makes exceeding requirement of AISC. So we need to be careful to longer BRB with the simple plate sections. Okay. Oh. So the later part, I'd like to talk about application with the BRBs. One is a damage tolerant concept. I already explained that approved by by 1992, Wada and Kona and Kawai and others. That is keeping a gravity supported structure in elastic, and the seismic structure in elastoplastic. It can be replaceable. Sometimes U.S. researchers call that it's kind of the hues. And that can be achieved that designing a BRB is the earlier, stiffer than main structures, and also the earlier yielding causes this the deformation between yield of the BRB to yield of the main structure can be the rooms for the dissipating energy without harming the damage of the main structure. So when we use low yield BRB and high strength main frames, this energy dissipation zone can be expanded. So much easier design for the damage tolerant concept can be achieved. So the first application is to achieved by Triton Square project in 2000. And the design by Professor Wada and Nikken Seke. And there are three the high-rise buildings providing BRB is to the between the column and the beams. And the BRB is the low yield strength steels, and the main frame is a high strength steel was used. And after that, in Japan, this damage tolerant concept is very becoming common. And in many the high-rise building in Tokyo or major city in Japan is using the BRBs for the dissipating energy concept. And the larger BRBF with reached several thousand kilonewtons is used for this construction. And not only high-rise buildings, low-rise building or mid-rise building can be to be applied for the BRB is applied for the damage tolerant concept. This picture is 7-story the buildings in Tokyo Tech campus and covered by the 4,500 solar cells producing their own energy in the sunny days. And this building is covered by the solar cell, but the main structure is like this shape. And to keeping the free, the brace-free, the open space inside the laboratory, and the BRB is to provide for the perimeter zone for dissipating energy. And the solar panel envelope is covering on the main structure, and their seismic capacity rely on the main frames. So this is animation for the left side is without the braces, right side with the braces to facing the Tohoku earthquake. And it's red one is the beam end is yielded, and the right side is only the BRB braces yielded. So the dissipating energy with keeping the main framing elastic. In the left side is the shaking is continues longer, and the damage is the beam end. That means the continuous occupancy is difficult for the right side because of the main frame supporting a vertical weight is damaged, while the right side only braces to be damaged or yielded, so it can be achieving continuous occupancy after the big earthquake. So this is the two model, ordinary frame and the damage controlled structure with additional energy dissipation braces. And the effect of the strength of the BRB is only 1/8 of the main structure, but even though the stiffness is higher than main frame, so all the energy is concentrated on the BRBs, and they can be the ordinary braces reach it is the point 0.7 or something for the percent radian for the solid drift angle. Sometimes damage on the interior frames. While the with the BRBs, the maximum solid drift angle is reduced by only most of the less than 1/3 to less than 0.2 or 3% radian solid drift angle. So for the larger earthquake of 500 years return period, the main frame, ordinary frame, is reached damage at the beam ends. That need to be that means building need to be huge the repairment or demolish after the earthquake is required. While the with the BRB layout, the maximum solid drift angle is still 0.5 the radian percent radian that means continuous occupancy is achieved by the interior wall is secured in the safe. So this concept is also used for the high-rise buildings in San Francisco. This the 181 Fremont Tower is providing a huge mega braces composed of the two dampers, viscous damping devices with primary BRB as center. And for the ordinary earthquake, the viscous damper dissipates the energy. And for the larger earthquake, the BRB is secure for the ductility for the whole system. So this concept is used for the retrofit of the buildings, and that we to propose integrated facade engineering. That is the additional the layer of the facade attached on the existing frames with poor seismic performance. So interior that inner additional to the inner scheme, seismic energy dissipation braces that the BRBs attached on the facade, and together with the outer skin control the thermal conditions. So thermal conditions is in the summer they cut the summer sun, introducing natural wind in spring and fall, and in winter they are producing heatness at the eaves. Condition and introducing sunlight inside the rooms. And for the structural conditions, the damage tolerant condition is achieved by keep the main structure in elastic and try to dissipate the energy by the additional facade by the elastic zone of the main frame. So this concept is applied to the Midoriga first building in Tokyo Tech in 1905. That was the old building is designed in 1967. That is has the column shear failure is expected for the larger earthquake. So ductility of the column is to be prevented by the additional carbon fiber wrapping, and the additional BRBs with outer skin is attached on the facade in the south part. And the upper part of the laboratory office for the including myself laboratories is keeping in inside the buildings while the construction retrofit construction was continued. So the BRB is up to the 1,400 kilonewtons is to attach it on the existing the buildings, and to additional the strength and stiffness is added by the additional BRBs. So the testing of the mock-up test was carried out with the same rebar arrangement. Because of the poor rebar arrangement, the shear failure of the clamp is occurred in the clamps to losing bearing capacity. While the covering with carbon fiber with additional BRB, they have a quite stable hysteresis can be achieved, and also their strength is very much increased. And also the summer conditions, the European countries sometimes using a double skin concept, but that is very hot, becoming hot without ventilation in tropical zone like in Japan and also Mexico. And we produce outer skin concept that is very effective to reduce the summer heatness in the perimeter zone. And also the in the winter they have a small the heatness include to additional heating at the lower glass part. So we apply this the concept. So the construction was done by the attaching transfer beam to connect the additional beam to the existing the structures, and with covering carbon fiber reinforcement, and so breathing will attach it on the surface of the buildings. So appearance of the buildings was to be improved very much. So that came to given the many design awarded after the completion of the buildings. So this concept is also the to interested in foreign countries. The Turkish school is considering BRB retrofitted. That we have to joint research was done with Istanbul Technical University, and we propose BRBs with existing the surrounding steel frame, elastic frames to put into the frames of the concrete walls. So that makes the BRBs almost also to improving performance of the frames, and also steel frame can be effective to reduce the residual drift after the earthquake. And for the truss structures, also the BRB can be applied to the spatial structures. When you pushing this kind of truss tower, they causes a buckling at the bottom. When it's reinforced, this members, another member can be reached to buckling. So no end for the to preventing a buckling for these truss structures. But if you replace the lower or only two part of the BRB, they yielded in the certain strengths. If these forces can be achieved by the stand with all the other members in without the buckling, the whole member system can be very stable. So this BRB have force limiting functions, preventing not only this member but all other member can be avoided from the buckling. So that is can be applied for the many gymnasium or the storehouses on the towers. So seismic retrofit of the communication truss towers. In the coming earthquake, some of the diagonals is expected to be buckled. So we replaced these members by the BRBs. That is a very economic seismic retrofit and also effective to preventing another ordinary truss members from the buckling. Okay. And for the roof structures, also known that only because of the horizontal input, vertical acceleration is excited, and the horizontal acceleration is excited in both ways. Complicated response is occurred, so that can be improved by the additional the base isolation roof, the devices attached on the supporting part of the roof, or providing the damping devices to the substructures. So in this concept, BRBs can be used for the improving the seismic performance of the roof structures. So this concept is applied to the actual buildings, like a Toyota Stadium. These paired the braces BRBs, and the Shimokita Dome, that is a membrane dome structure, providing a BRB on the roof surface, together with supporting the frames. And BRB also spine concept. So when we distribute BRB in each stories, if the damper fractures in certain strength, the story collapse or story damage concentration can be occurred. So in 2011, the American, we are working with American researchers for the concept of the control locking system that are providing a spine into the clamp with the locking actions, and the self-centering function is secured by the PT wire to pushing into this, and the energy dissipation hues like BRBs, including a BRB, can be provided to the connection between locking frame. So this concept is also expanded to the another the spine system that is the material research buildings in Tokyo Tech in the Suzukageda campus. I put it the locking spine frame is at the center of the buildings, and this locking frame is supported by the buckling-restrained clamp and the braces, and they dissipate the energy, and they also distribute the damage for all the floors. So the BRB can be attached on a locking position of the spine frames. So comparison between these shear the distribution, they display fully hysteresis. The American locking frame have the flag hysteresis, have a complete self-centering function. This non-uplifting spine is producing fully hysteresis, but there is no function for the self-centering functions for the spine itself. But in Japanese practice, keeps main structure in moment frame. So this elastic stiffness can be to make some self-centering functions. So the comparison for the shear damper system, lift-up spine system, non-lift-up spine system, this is maximum story drift angle. Here the residual story drift angle. So this shear damper system is causes some concentration at the second floor, and but both spine systems have a very evenly distributed story drift angle, and also the much smaller residual story drift angle. Sorry. That makes very high performance for the continuous occupation after the larger earthquake. This concept is also the used for the retrofit of steel frames, inserting the RC core clamps supported by the BRBs in San Francisco by these people, Mr. Tippingmar or others. BRB is also the apply for the dumped outrigger system. Dumped outrigger system is known as to reducing not only acceleration and also the displacement, and BRB can be applied for this system. This the BRB dumped outrigger is applied for the example like Urisha Grand Tower in Los Angeles, and you can see the large BRBs and the in the hotel lobby and the office zone. In dummy tolerant structure, I explained that the BRB can be to replaced after the earthquake, but actually replacing a BRB is not easy. This buildings was completed in 1998, but that hit by the buildings stand in Fukushima prefecture and received the 2011 Tohoku earthquake at very high intensity of the acceleration. And there was a cumulative deformation meter, and the maximum deformation meter is attached on the BRBs, and we measure that some the yielding of the BRBs observed like yield ratio of the 4, and the cumulative plastic strain reached to 20%. But that is only 6% of the fatigue capacity of the BRBs, and there is no residual deformations. So we have the client is satisfied with keeping use these BRBs after the earthquake. So there is no replacement was occurred. So in good BRBs, actually can be stand with several the times of the larger earthquake. So I believe that in many cases, BRB can be stand with the end of the life cycle of the building itself to keeping the energy dissipation capacity, even though the yielding in the earthquake to keeping the main structure inelastic. So we have also the designing another the campus buildings in the Tokyo Tech, now the Science Tokyo. That is our architectural buildings with their cafeteria is to covered by the BRB as an interior. And we have a nice studio at the top of these buildings. Okay, so that is my talk, and the BRB are easy to use and can be applied to a variety of structural systems once the component design has been carefully considered. So, thank you very much for your kind attention. That is my the talks.
Thank you.
Thank you.
very much.
Thank you very much, Professor Takeuchi.
Thank you, professors. This is a real good and astonishing contribution. We really appreciate your talks. There is a few questions, and I don't know if we have some time for one or two questions. Do you have some time, professors? Professor Wada, Professor Takeuchi? I don't know if you can hear me.
When you mailed us, we will respond.
Yeah, I can read the questions if that's okay for you.
Mhm.
Okay. I will start with the very first one. Carlos Badajoz says that he would like to ask your opinion about the following. Is it necessary for the structural connections to be moment resisting? in order to use BRBs as energy dissipating elements?
Professor Takeuchi, please.
Okay. In Japanese practice, using the BRB with a moment frame. But I understand in many the American or foreign countries using a moment frame or BRB, and sometimes the BRB is attaching on the pin-ended the frames. So, but I think in damage concentration views, it's not good. So, as I explained for the spine frames, moment frame is important. Elastic moment frame is important to distribute the damage to the story. So, I strongly recommend BRBs with elastic frames.
Yes, I think also.
This is also a common practice in Mexico,
Mhm.
and we use that kind of system. But what do you think about the connection to the weak axis? How do you solve that in Japan?
Okay, so in Japan, the BRB connections is out of plane rotation stiffness can be recommended to be stiffer, but it's in sometimes it's difficult for the weak beam or weak clamp. So in that cases, we recommend to keep the moment transfer capacity at the restrainer end.
Okay. There is another question from Daniel Jimenez. He asks, how do you control the beta factor in long BRBs during design to avoid the core bending effects?
Thank you for the good question. We are trying to investigate how to avoid ending the core end binding. So actually, core binding is not affect on fracture, the fatigue performance of the BRBs, but in increasing compression stiffness, damage on the connection on or instability or damage on surrounding beams and the columns. So we recommend to increase a little bit the thickness of the debonding materials at the end of the core plate, but we also need to keep the moment transfer capacity of the at the core end. So we are now investing in how to improving this kind of effect effectively.
Thank you. We will read one more questions because we are out of time now. If you don't mind, we are just selecting one of the questions. Let me think. What do you think is Jose Luis Gonzalez asks, what do you think is the best position or the most efficient positions for BRBs? Totally horizontal, inclined, vertical? What do you think?
I mean, the position of the BRB.
Yeah.
I personally recommend providing a BRB as on the outer the diagonal or the diagrid system. That is very effective to keep the stiffness and the comparison compared from the core areas. Its vertical layout is losing their effectiveness by the bending effect. So outer diagrid skin is most effective, I recommend. But that need to be a deeper discussion with the architect that appear to the appearance. It can be the answer for that.
Yes, thank you very much. I don't know if you have any final message, professors, to say goodbye.
Please, Wada.
Yes, I visited Mexico many times, and I'd like to visit again. I like Mexico. Thank you.
Thank you very much. Gracias.
Gracias. Thank you. Thank you very
Thank
much.
you. Gracias.
It was really nice to have you here and hope to see you soon in Mexico.
Yes, yes. And please come to Japan also.
For sure. Thank you. Thank you very much.
Gracias.
Thank you very
Adiós.
much.
Adiós. Thank you.
Thank you.
Nos vemos el jueves los demás. Gracias.